Hi, my name is Ehsan, and I'm going to present our paper, Divergence-Based Motivation for Online EM and Combining Hidden Variable Models. This is joint work with Manfred Warmuth, done at Google Brain, Mountain View, California. Let's first consider the setup. We have a hidden variable model. Given samples V from an underlying data distribution PD, we would like to minimize the negative log likelihood of this model. Here, V denotes the visible variable, H denotes the hidden variable, and theta tilde denotes the model parameters. Notice that the marginal distribution over the visible variable involves an integral or a sum over the hidden variables. This makes the negative log likelihood more challenging to directly optimize. Instead, the EM algorithm forms an upper bound of the negative log likelihood by adding a non-negative divergence to it. We can also rewrite the EM upper bound as an expectation over the log of the joint distribution over the hidden and visible variables. In summary, the EM algorithm proceeds iteratively in two steps. In the E step, it forms the posteriors and calculates the upper bound, and in the M step, it minimizes the upper bound. We will now rewrite the EM upper bound in a way that will involve sum of divergences. First, consider the following joint distribution parameterized by theta n. It involves a Dirac measure centered at Vn over the visible variable, multiplied by the conditional distribution of the hidden variable given the visible variable. We call this the Singleton Distribution since it puts all the mass at a single point. Now, if we calculate the relative entropy divergence between the Singleton distribution and theta tilde, we end up with a form that is very similar to the EM upper bound. In fact, we can rewrite the EM upper bound as sum of relative entropy divergences from these Singleton distributions to theta tilde. This divergence-based view of the EM upper bound allows us to revisit online EM algorithm in a new way. In the online setting, we receive a small batch of samples Vt at iteration t. We then minimize the negative log likelihood plus an inertia term whose role is to keep the new parameters close to the old parameters. The inertia term that we add is also in form of a relative entropy divergence. Following our discussion, we end up with sum of batch size plus 1 many relative entropy divergences. This ends up being very similar to the batch EM algorithm, and in many cases will have closed form solution. This divergence-based view has two main implications. First, we can view it as a natural gradient descent step by first approximating the relative entropy inertia term by a quadratic, in which the Hessian is the Fisher information matrix. Therefore, we can view one step of the online EM algorithm approximately as a natural gradient descent step on the negative log likelihood. Secondly, we can perform approximate updates when there is no closed form solution for the inertia term. This involves drawing samples from the model distribution and forming a new upper bound. In the paper, we derive closed form updates for mixture of exponential families, hidden Markov models, and Kalman filters. Notice that the upper bounds for these models, which are from exponential family, will involve Bregman divergences. We also derive approximate updates for the compound Dirichlet distribution. And to solve this, we apply the iterative Newton's method to optimize. Finally, the divergence-based view of the EM algorithm allows us to combine models in a distributed setting in a more systematic way. That is, we minimize a weighted sum of relative entropy divergences from these models to our final model. In the case where these models belong to the exponential family, this involves averaging the complete data sufficient statistics. In the paper, we validate our online EM results by performing experiments on a set of synthetic datasets. We also apply our results to learning Gaussian mixture models in a distributed setting on a standard dataset. In summary, we unify the sample level and model level of the online EM algorithm. This allows us to derive updates for more complex models such as HMMs and Kalman filters. Also, it allows us to perform approximate updates when there is no closed form solution for the EM update. Finally, the divergence-based view of the EM algorithm allows us to combine hidden variable models in a distributed setting. The long-term goal of this project is to extend the current results to more complex hidden variable models such as GANs and autoencoders. Thank you for your time.